you use it. And over here, I'm just going to focus on, right now we don't have two electrons, truly two electrons, close coupling calculation. What I'm trying to say is that, if you look at, let's say you want to capture two electrons into, doubly charged ion, for example, alpha particles, right? So in the calculations, close coupling calculations become extremely difficult because you want to keep track of that two electrons, right? Okay, so it's notoriously difficult to do charge exchange for two electrons. Okay, right. My talk is going to be very compact, so this will save a lot of people a lot of time. And so I'm going to present you go into the theory part, the concept. Okay, so please, if you are not interested, just take a nap, please don't run away. Okay, so I'm just going to show you two methods. One is that we use, the two-center atomic orbitals close coupling that we apply for intermediate to high energies when we say, that would be from a few tens of keV up to about 1 MeV. Okay. Then we are going to go down to lower energies, like a few keV-ish, right? And then it's going down to 0.1 eV, right? Then I'm going to show you the applications and a very short summary. All right. So now, high energy. So when I say high energies, this is about a few tens of keV up to 1 MeV. So in this case, we solve so-called the time-dependent Schrödinger equation, and because let me define what do you mean by high energy. So high energy means that when you have these charged particles, your projectiles coming in, right, and the velocity of this projectile is way faster compared to the orbital, initial state velocities, initial state electron velocities, okay, way faster. So when you come in this case, you can use a semi-classical approach using the impact parameter representations. So this picture sort of, conceptually represents what is going on, right? So there are many ways of solving these Schrödinger equations. One is using the, close coupling, or some people like to call it coupled channels method. Or you can discretize the whole thing, the whole Schrödinger equation in real space, okay, in a box or whatever you like, okay. Now, of course, there are many ways, a few more ways to solve it. Now, here is what I call a two-center atomic orbital. Actually, Igor already showed you, what do you mean by two-center here. So here, this is the atomic. This is not atomic Hamiltonian, but this is the Hamiltonian of the system, right? So now you're going to expand to solve this time-dependent Schrödinger equations, right? So you're going to expand your wave function in terms of the basis set, right? So here's the thing: you're going to expand it in terms of the projectiles and also in terms of the target, right? Now these orbitals here, again, you expand them in your desirable basis functions. It can be Laguerre, it can be Slater, it can be Gaussian. It depends on the problems that you want to solve. Okay, why people would like to use two centers is because you can actually solve the problem in a unified way, which means that you can, if you try to get electron capture, electron excitation, you want to get ionization, you can do that. Okay, you can do that. But you have to be very careful when you solve this problem because the basis set is the key. Okay, the basis set is key. These atomic orbitals, you're going to have. It has to satisfy your atomic Hamiltonian, which means that you're going to get a spectroscopy states, and then after that you're going to get a pseudo states, and you're going to get some continuum. Okay, it should form a complete set. Okay. Right? So, can you hear me?
Yeah.
Yeah, you can hear me well. Okay, so I don't need this. So now, if I put that basis set into the time dependent Schrodinger equations, this is the couple differential equations that I'm going to get, right? So the question here is, you're going to, this basically, if you look at it, this is actually your overlap matrix element, right? Okay? So to calculate all these matrix elements accurately, is not that easy, because you've just imagined that, suppose you have these orbitals here, this orbital is continuum, right? It's highly oscillating, and then your lower states, you probably have n equal to 2s, 2p, whatever, right? So you're going to basically overlap highly oscillatory functions with a sort of a exponential decay. Okay, that calculation you can do that, but when you want to overlap continuum states, the calculation is not that easy. So oftentimes people get into a problem with doing this. When you integrate this matrix elements not accurately, you're going to get some problem in your calculations. Okay? Now, so the key point is to solve this couple channels differential equations, right? So you basically time propagate this equation to a very large time, because you start from minus infinity time. So the ions come in, right? And then it's coming very fast, then it's going to collide, it's going to capture electrons, right? And then it's going to move away. Now, these orbitals here, right? These orbitals, in order to make the electron hop from the target to the projectiles, you have to put in what we so-called a translational factor. Okay? Artificially put it in. So basically, the orbitals that you saw just now, right? There's an electron translation factor here, because electron somehow has to follow the motions, of the charged particles, right? Otherwise, your electron will not be able to hop. So there is sort of also, an issue when you want to do low energy ion atom collisions, okay? Because anyway, now if we propagate, so we want to time propagate this, couple channels. Couple differential equations to large time after the collision is done, all the processes is done. So then what you do, you project out, your basis states, right, to get your transition probability, right? From a transition probability, then absolute square. This is actually a complex number, okay? So you take absolute square, you're going to get your transition probability here, okay? Now, to get the cross sections, you basically do these integrations. Okay, this is sort of this is very textbook, right? Now, to do low energy, so we have to think about, because okay, what do you mean by low energy? So it's opposite of high energy. I'm sorry, it's a bad joke. Well, low energy means that the ion come in very slowly, right? Relatively slow compared to the initial state orbital motion. Okay, so you can imagine that. So what's going to happen that when ions come in slowly, and then it's going to gradually interact with the target. So which means that electron is actually, I'm talking about one electron problem here. So electron has the time to share between the two centers. Okay? So in this case, you cannot use atomic light descriptions. Okay? You have to now go back to your Born-Oppenheimer type of description, molecular descriptions, in order to do this problems. Okay? Here I'm going to because in my group, in Chidong's Lin's group, we are familiar with these hyperspherical methods. So we would like to use hyperspherical methods. So hyperspherical methods, it went way back in maybe even 1960s. It was used to study WSIO states and photoionization later. It was used for a qualitative explanation of the physics. Okay, the physics is more important if you follow Farnell's group, physics is always more important than all these calculations. But then with the advance of a computer, then hyperspherical method become more and more powerful. Okay, powerful enough, but not that powerful yet. Okay, now we want to use this method. If you look at, so we want to write. Actually, this is what is happening. You start with this type of configuration, right? So basically, you have ion, and then you have atoms, right? These are alpha, what we call the alpha set. Okay, alpha coordinates. Now, what will happen next is that if you have elastic or excitation, the configuration is look like this, right? The beta set, right? Now, next, if you have a charge transfer rearrangement, you're going to have your final state is rearranged. So that's why charge ion atom collision, rearrangement collision is not that easy to do, because your final configuration changes. Okay, at large distance. Okay, you somehow have to change, rotate or orientate your system. Okay, so anyway, so we want to use this so-called the mass-weighted hyperspherical coordinates. So we write down, this R here is our hyperradius. Okay, mu1 is actually the reduced mass of A plus, and B plus. Okay, but mu2 here is actually your central mass of A and B to your electrons. Okay? Now, this mu here is actually is arbitrary. So in this case, if you imagine that if I choose mu to be mu1, then this guy goes away. This is very small. So your R essentially, is very close to rho 1, right? So this is basically like your internuclear separation. It's like your Born-Oppenheimer. So it's analogous to, this theory is analogous to Born-Oppenheimer. Okay? So this angle here, theta, is defined what we call as hyperangle. I don't want to go into the details, but it's defined by these equations. Okay? So the nicest thing about using this method is that first you get rid of this, you get rid of this electron translation factor. Okay. Now another thing is that you also, if you use a conventional Born-Oppenheimer approach, okay, so you do not because Born-Oppenheimer essentially the first approximation is that you assume that most of your nuclei is infinitely heavy, right? So in this case, we take into account of the mass. Okay. Now, it's not important if you want to do heavy ions collisions, but it is important if you want to look at, for example, the deuterium plus and hydrogen collisions, because deuterium and hydrogen, the mass difference is very small, right? So it's like 3.7 millieV, right? If you don't do that, if you don't take mass into considerations, when you calculate the potential curve, the adiabatic potential curve, right? You're not going to get that asymptotic separations. Okay? So that's the key idea. So we want to do that. Probably it's overkill for multiply charge ion, but that is the, when we develop this method, we have in mind that, we want to include the mass in there. Okay? Now, also this method is what we also call a unified approach. So which means that it allows you to get elastic excitation in principle, and also it allows you to get the charge exchange cross sections. Okay. Over here, I'm not going to talk about three-body breakup, which means that when ion come in, anyway, three-body breakup in this low energy is not important, because basically you have ionization is very small. The ionization cross section drops like a rock. When you go down to lower energy. Okay. So that's why I say please don't run away. Okay. So if we write down the wave function in that way, right? So your psi here, the total wave function, satisfies your Schrödinger equation given in these expressions. Okay. Now here is what we call the Idiomatic Hamiltonian. This is very similar to Born-Oppenheimer. Okay, so here this lambda term is what we call the grand angular momentum, and is an operator that operates on your theta and phi. Theta is basically the angle between, you can think about it as a dot product between your rho 1 and rho 2. Okay, that's and this C omega here, don't worry about it. So this C over R is actually your total Coulomb interactions for all three particles. Okay. Now to solve this Schrödinger equations, we want to, like Born-Oppenheimer, we're going to expand it in terms of nuclear wave function and your electronic wave function plus this, d function. This allows your, wave function to rotate. Okay? Right? Yes, sir.
Just a question. You need to have a fast and slow variable.
Yes.
Hyperangle look like the fast variable, yeah, for you.
Yes.
Yeah. In this case, what kind of parametrical? Yeah.
Parametrical. Yeah. Thank you for pointing that out. Your R here is our parameter. It's our slow variable. Yeah, it's a slow variable. So it's like Born-Oppenheimer. We want to take advantage. Basically, the concept is just the same as the Born-Oppenheimer. So R is a parameter, so adiabatic parameter. Okay. Now, so in this case, first we calculate the potential curve. So Phil yesterday already showed you the potential, some of the potential curve using Born-Oppenheimer, type, and this potential curve is based on hyperspherical type. Okay. So essentially, they are very similar. Okay. Now, you diagonalize that Hamiltonian. You go back. This U is actually your potential curve. Okay, I'm going to show you that later. And then you project out this idiomatic basis function, right? And you're going to obtain this, couple channels. Okay, this is a radial equation. So basically, you want to solve for this. You want to solve for your f of r, right? Now, two ways of. Let me comment on this. If you do Born-Oppenheimer, you're going to see an equation that looks like this, but here you have these non-adiabatic couplings or rotational couplings, or you can think about it. You have a wave functions here, right? Channel functions, right? When you get if you want to operate, or you want to differentiate the wave function. If the wave function is very smooth, you can differentiate, easily, right? You can take a finite difference. But if your character of the wave function suddenly change when it's close to avoided crossing, right? You want to take that derivative is not that trivial. Okay. So in this case, we use a method based on this R matrix propagator and another method using slow variable discretizations. And this method has been developed by Tostikin, Watanabe, and Matsuzawa. Okay, so the R matrix method went way back to Phil Burke. Okay, so then what we do is that we solve this, propagate the R matrix to a very large hyperradius. Okay, and then from there we do like any scattering theory, we just met at asymptotic boundary. Okay, we match it to the atomic states. Okay, proper atomic states. Okay, then from there we get the K matrix, and then you get the charge, hence the charge exchange cross sections. So now, here's the thing: because non-adiabatic couplings is not easy to calculate, so we somehow change the equation so that we have that non-adiabatic couplings inside the overlap. Okay, so now we deal with the overlap rather than deal with the wave functions. Okay, so now why we want to do diabatizations? So many years ago, we learned this from Brad Esri and Hossein. Did the antiproton on hydrogen, look at the plutonium formations. They calculated all these potential curves. There are a lot of adiabatic potential curves, but we know that from experience from Hussein that only we there are only a few channels that is strongly coupled to the initial channel. Okay, so we want to find a way to eliminate those weak couplings. Okay, so that's why we resort to these diabatizations. Okay, in actual fact, you have to solve. Well, the diabatic basis is related to the adiabatic basis through that C matrix. Okay. Now, in order to get this diabatization, you have to solve these equations. But here, we are not doing a strict diabatization. We're just going to approximate it using the P matrix given by the overlap. We play with the overlap here. Okay? And then, so, let me say again, there's no non-adiabatic couplings here. It's just that we want to diabatize. We only want to diabatize where we have a lot of avoided crossing. Where there's one set of avoided crossing, we want to diabatize it. Because if you diabatize the whole, the whole range or the whole hyperradius, most of the time you're going to lose your adiabatic. After you diabatize your adiabatic channels, you're going to lose that, adiabatic channel, the character. Okay, if you do the whole range. You understand what I'm saying? If you don't, then...
No, we understand. You mentioned that only near pseudo-crossing important
yes,
this stuff.
we want to
if
start...
you're outside, all term, adiabatic term...
Right.
Phase comes.
Yes.
Thank you.
Okay, thank you. So, okay. Like I said, I'm just going to show you the application. So, this one, there are a few examples that I want to show you. This one is for high energy collision. So the energy starts from maybe 1 keV up to a few hundred keV. Here I'm using atomic orbitals. Okay, again, I'm looking at 1 electrons only. Everything that I do is just using 1 electron approximation. Okay, it's a frozen core, but it's just 1 electron. So the one that just now Peter showed that there's 2-center close coupling calculation done by Liu. When they talk about 2 electrons, they're basically using a frozen core. So basically they consider only 1 electron. Of course, you can always model your 2 electrons, okay, using different type of model potential. Okay. Right. Let me show you what this example here is that we have alpha particles colliding with sodium on the ground state. So this picture shows some experiment measured, maybe 10 years ago, and this paper was published in 2006. Okay, it's quite a while ago. So the 2-center atomic orbitals close coupling, agrees pretty well with the experiment, and then you have the CTMC calculations, and you also have this Sturmian atomic orbitals calculations. So these for charge transfer. So in the 2-center close coupling calculation, I only need to do 1 calculations. Okay, I only need to do 1 calculation. I can get, for each energy, then I can get total charge transfer, state selective charge transfer, excitation, and ionizations. If I do it right, otherwise, then then my theoretical curve or theoretical answer will not be the same. Will not agree with other theoretical or even experiment data. Okay, so the key is to be able to actually control your basis set expansion, okay, properly, because after all this is a Coulomb interaction here, okay? Except in this case it's a model potential. So over here I'm showing you ionizations ratio to a single capture. There's an experiment data here, right? Go down to relatively low energy to about 2 keV or so, and you see that the agreement is pretty good, okay, with the experiment. Now, this is state selective This is partial n equal to 2. Okay, and you can see that CTMC is kind of high. That's the blue line. But AOCC, all the AOCC calculations sort of agree with each other, right? So you go to higher n equal to 3, AOCC, both AOCC actually agrees pretty well. And then n equal to 4, now CTMC started to pick up, right? Okay. Now, when you go to n equal to 5, n equal to 4, greater than n equal to 4, so I sum all the n equal to 5, n equal to 6, n equal to 7 up, all the states, this is what I see. Okay? The red line here is not that the Sturmian AOCC is not working, but I think the basis set is not converged. Okay? Right. Now, to take a look at this example again. So this is NL charge transfer. So this is 2s and 2p. So I compare with another the Sturmian AOCC, and the agreement is not that, it's not perfect, but it's not that bad. Okay, at least now we know, this AOCC is working. Okay, okay. Now we look at different system. For example, beryllium 4 plus on hydrogen captured to beryllium 3 plus 2l state. So this is captured to 2s, and this captured to 2p. So here I'm showing the lattice approach, AOCC, CTMC, and MOCC. So you can see that the agreement of these 4 methods are pretty good, right? Except at low energy, CTMC is slightly higher. Right? Now you look at this one, for the 2p captured 2p, all these 3 methods except the CTMC at low energy, is slightly is kind of off. Okay. Now also look at capture to 3L. So there are 3 different methods here. Let me make one point clear here, is that we build the basis set, and then we use that same basis set for all the energies, right? Now, this line I'm showing you, this is actually a relative cross section. So relative to what? So this will be AOCC relative to lattice time-dependent Schrodinger equation, and then CTMC ratio to lattice time-dependent Schrodinger equation, MOCC lattice. Okay, that's the ratio. Now, the key point here is that most of us agree, except the MOCC because MOCC, we know that the molecular orbitals work for low energy, so we can understand that. If you start to deviate, we can understand. But you can see that AOCC and CTMC agree pretty well up until very high energy. So up until this, about 1 MeV, this is 1 MeV, or even like maybe 4 keV or so, 400 keV, sorry. The basis set may not be that great for which I optimize it for low energy. So in this case, you have to go back and re-optimize your basis set. Okay, let me put it this way: if you know what you're doing with your basis set, right, you can definitely get a converged result. Okay. What I'm trying to say is don't do it blindly. Now, look at this. We examine it for this is n-dependent and also as a function of energy. So there are 3 theoretical calculations here. So we keep on pushing this AOCC method basically to its limit, actually. So, and you can see that the agreement is not bad. I hope I convince you. Right? So this argon 18 plus, they show you one plot of, a couple of plots of them, and this is showing that the black line here is using CTMC, and then the dotted line is using AOCC. So basically, this is showing you the L distributions. You have basically N and L distribution. So you can see that, it's not like CTMC. You get a block like this, a block like that, but there's some distributions. Okay. So like Yuri said, this is quantum mechanics, right? So P wave, P state, D state has a different, capture probability. Essentially, that's what it's trying to say. Okay. So of course we cannot calculate up to n equal to 11. That's too big for us. Okay. Right. So this is the n distributions comparing CTMC and AOCC. Okay. The agreement is reasonably good. Right. Now, I'm going to switch gear and go down to low energy. Now, oftentimes for low energy, there's no other theoretical calculation, or if there are, there are not many. So we can say that we don't really know what is the cross section actually look like, whether it makes sense or not. So that's why we need potential curve. We need potential curve. It allows us, by looking at the potential curves, it allows us to understand what's going on. And whether the cross-section that we get makes sense or not. Because you have no other ways, not like you don't have CTMC to compare. If you compare CMC, you're going to get, huge, heaven and earth difference, right? So we need to rely on something that we understand. We hope we understand, okay? So let me talk to you about this proton on deuterium as as an educational example. So here's the point. This is actually adiabatic potential curves, right? So asymptotically, right? So when you calculate this asymptotically, this is your entrance channel, okay? So then you're going to get electron excited to here or promoted to here. I don't want to use the word excited. Get promoted to here, right? And then promoted here, also you can promote up to higher states or higher levels, okay? Through, rotational coupling, right? Now, if you do conventional Born-Oppenheimer, right? You do conventional Born-Oppenheimer, you treat the two center masses infinitely heavy, you're not going to see these separations. This separation is 3.7 millieV because of the mass difference. Okay? So, now, these are the potential curves, and over here, all these H and D and H, they separate into n equal to limits. Okay? These are dissociation limits. Right? Now, let me show you, this is the total capture, sorry, not total. So this is captured to 1s cross sections. So this is hyperspherical, right? I'm only using 4 channels here. I show you over here is something like 8 channels, but I only use 4 channels. I pick the channels. Okay, I pick the channels where I think that when the couplings are important. So I pick these 2 channels and another 2 channels up there. Okay, I use just 4 channels, right? But there are almost thousands of partial waves. Okay, we want to reduce the number of coupled channels, but because we are using partial wave expansion, so the partial waves, we want to include all the partial waves that needed for the calculations. Right? So this is the result, single captured to 1s. So you can see these are experimental data, the black points and the square. And then this is the time-dependent, semi-classical time-dependent density functional theory calculation down to 1 eV. You can see that it started to deviate from this straight line. Okay, there's a problem here. Okay. Now, this Alex Delgado calculation, see that dotted line? And I tell you this, it was done in 1950s. Okay, it's way back. So
Before invention of computers.
before the invention of computer. So it's kind of really impressive. Yeah. Anyway, oops. Okay. Now, this is captured to 2p and excitation 2p. Now, the question here is, you know that capture, the cross-section is going to go, and then it's going to come down. Does it make sense? That's the question. Okay? So by looking at the potential curves, okay, now we know why is this. Now, I'm putting here, if you look at, let's say, 30 eV. Let's go to 60 eV first, right? Why the cross-section drops, okay? So if you go to 60 eV, if these are potential curve, these are 2p sigma and 2p pi. So the transition is through rotational coupling, okay? So if you look at there, you see the energy gap is very tiny, right? So the rotational coupling, basically the transition is very efficient because you have a very small energy gap, right? You can go from one state to another state, without any effort, right? Now, if you go down to 30 eV, so this gap become larger. So to promote from here up to here is not that easy, right? Okay, so that's why your cross-section rate started to drop. So if you go down to even lower energy, your gap become larger and larger and larger. Then you don't have the energy to get promoted, to the next level. Okay, so this is through the adiabatic potential curve. Right? Now, let's look at carbon 6+ on hydrogen. So here, I show you these adiabatic potential curves, right? And then this, if I look at this region, so that's n equal to 4. And then this region here, the avoided crossing, pseudo crossing here, okay, that's n equal to 5. Okay? Now, like I said, we choose the diagonalizations, so we choose to diagonalize this area and this area. Okay? So now we calculate the cross-section. This is how the cross-section looks like. Okay? So n equal to 4 and n equal to 5. N equal to 4 is always larger until you get to this point. And n equal to 5 is always smaller. Why is that? Can anybody tell me? No? Oh, right. Just imagine, if you come in through this line, right? You just imagine you drive very fast, right? You come in this high energy, right? From 1 kV down to let's say, few tenths of 50 eV or so, right? So this is very relatively fast. You drive, you pass through this place, right? You straight go here. This n equal 4, right? So that's why everything that happened at high energy, you will straight go into n equal 4 first. So that's why n equal 4 is you have a large cross sections. Okay. Now, okay. Now let's take a look. Now, because n equal 5 is your second dominant channel, okay? So let me tell you why atomic orbitals does not work. You have to either use molecular orbitals or hyperspherical orbitals. Okay? Here's the reason, right? You know that there's a voided crossing at somewhere, I don't know, here, about 24 internuclear separations, pretty far, right? Now, then you come in, everything you populate, first you populate this guy if you come in very fast, right? Now, how do you populate n equal to 5? Well, you come in, in order to populate that is your population, that is you have to go to very close internuclear separation in order to populate n equal to 5. All your couplings are right there. Okay? So that's why if you do an AO calculation, no, it doesn't matter how many, if you dump in the whole kitchen sink in your basis, it will not work. Okay? So that's why we found that AO method will not work if you want to do a weaker channel. All right? Because everything happens in a very small internuclear separation. Okay? This is one example. So now I move on to oxygen 8+. On hydrogen, basically the story is the same. We use the diabatization techniques, to remove some of the weaker channels, and we left with 7 channels, with thousands of partial wave. Then we calculate the charge transfer cross section. This is the total charge transfer compared with the different theory, right? And then there's only one set of experimental data. Okay, the theory agrees pretty well with the MO calculations, right? At high energy, when it started to come down here, this Kimura calculation it did long time ago. Okay, then there's another set of MOCC calculation done by Shippey or Green, can't remember their name, but we agree with their calculation. We suspect that Kimura calculation here, the basis set is not enough. Okay, at low energy for their molecular orbitals method, right? So this is to look at n equal to 5 and n equal to 6, okay, distributions. So we compare different theory again. Okay, the AOCC method in 83 does not really work. Okay. So this is actually the world view or the bigger map. We're looking at this cross section for n equal to 5 started to drop, and n equal to 6 is small but started to pick up. It started to become important. Okay, for lower energy range. I know that you guys are interested in, basically this energy range, right? So, but you also need to consider, this part, n equal to 6, start to pick up. There's a crossover between n equal to 5 and n equal to 6. So it's always this type of case. Now, argon 8+. This is using a model potential for argon 8 and hydrogen. All right? So we can calculate all the potential curve. Again, we can split them out, look at different states. This is the capture cross-section to 6L, and then there's the 5L. Look at the distributions. Okay? Argons, these are n equal to 5 and 6 partial cross-sections. This is how they behave. And then finally, neon 10+ on hydrogen. Similar. So here's the thing: the heavier system that you go, the more channels that you'll see. Okay. And because we can eliminate the weak coupling, so this one allows us to calculate. It will allow us to calculate the cross section quicker, okay, more efficiently. So this is n equal to 5, n equal to 6. So n equal to 5 is very small. Again, n equal to 6 and n equal to 7. And the total is the dashed line. Okay? So at least we understand our cross-section makes sense through potential curves. Okay? Right, this is the summary. So the key point here is that the hyperspherical methods allow us to examine the potential curves and to help us to understand basically, I would say the behavior of the cross-section as a function of impact energy. Another thing is that for low energy collision, AO descriptions for weak transitions will not work. Okay, that's basically the take-home message. So I hope I do not disappoint you. I know that you're also interested in spin-dependent calculations. Right now we have the capability, but we need to develop on it. Okay? Thank you.
Any questions?
There were a lot of equations, and the word hyperspherical
Yeah.
was used many times. But bringing this to one of the observational ones, there's a lot of outstanding questions about oxygen, bare oxygen recombining with either hydrogen or helium. And especially two questions, which end state does it fall into, and the L distribution. Because essentially there's the oxygen lines that show up seem to not quite match, the simplest possible theories. So my question is sort of, is this suggesting that the simplest approximal, the Q to the 3/2 approximation, starts to fail? Does it go to higher end states as you go to lower?
Yes, you go to lower energy, as you can see, you go to low energy, so it started to, the behavior started to change, even like neon, for example, right?
Okay, so
So this n equal, you look at it, this n equal to 6, right? At about 1 keV, so you can see this is sort of a dominant, but n equal to 7 is not. But when you go down to lower energy, so n equal to 7 start to pick up, then you're going to drop, n equal to 6 is going to drop. You see, it drop like 4 orders of magnitudes. So which means that you, in your model, you need to consider this. It's energy dependent, it's not.
But 100 electron volts, it's not astrophysical issue. Yeah, certainly we have a large energy of collision, kilo electron volt.
Right.
It's reasonable. Yeah. In this case, it's agree with common result. Yeah.
Right. So, Phil?
Well, Randall kind of asked, but the problem with your hyperspherical calculations is no L resolution.
Exactly. So, to get the L resolution, basically what one needs to do is to project onto the dipole states. Okay, as asymptotic. You have to separate that out, to get the L resolution.
Yeah,
I mean, L distribution. Sorry.
Not getting dynamical.
Sorry?
That's not dynamical probabilities in the L. You're getting just at the end.
Yeah, I'm getting at the end, not the dynamical.
Why don't we save any further questions for the coffee break, which will